Hello everybody, I'm Ammar Elwafy. In this video we are talking about page replacement algorithm and comparative performance study, understanding visual memory management in modern operating system. Presenters Ammar Elwafy, Alzubair Alsalehi, Muhammed, Salim. First, visual memory enables programs to exceed physical memory limits. Visual memory is a fundamental abstraction that allows processes to execute even when it's not fully loaded into the RAM, bridging the gap between either infinite memory, which is virtual memory, and the real-world hardware constants, which is RAM. First, modern applications demand and requires increasingly larger memory footprints, making visual memory management paramount and more essential to system performance. Memory hierarchy consists of fast but small cache and moderate speed RAM and slow but large secondary storage like disk, SSD, and HD, etc. Operating system use demand paging to load pages from disk only when it accessed, triggering or doing a page fault when the required page is not in the RAM. The critical performance challenge arises or happened when memory is full and the operating system must select a victim frame to evict or delete. Page replacement algorithm PRS determine and choose which page to evict or delete, directly impacting system efficiency. It makes the system efficiency more and make it faster to perform. Second, we have a page fault create massive performance bottlenecks. If we look at this equation, the effective access time is equal to 1 minus b, the page fault rate, multiplied with a memory access time, plus b, which is page fault rate again, multiplied with pft is page fault time. If we look at here, memory access, it's a fast access to RAM. It executed in a nanosecond, and the disk is a slow access to storage. It executed in milliseconds, means it's 10 times slower than the memory access of the RAM. The critical disconnect since disk is orders of magnitude slower than the RAM, keeping the page fault rate extremely low is essential and important. Inefficient algorithms using may cause fracturing, where the system spends more time swapping pages than executing instructions. First algorithm of the page replacement algorithm is first in first out algorithm. First in first out algorithm is a simple but suffers from Brady's anomaly. First in first out algorithm manages pages as a simple queue. The oldest page in the memory, which is the head of the queue, is always chosen for replacement. It has advantages and disadvantages. First, it's easy to implement and low overhead, minimal hardware requirements. Disadvantages of it, its poor performance, fails to recognize that heavily used pages might be old or it's recently executing. Brady's anomaly. Brady's anomaly is a counterintuitive phenomenon where increasing the number of physical frames results in more page faults. As you can see here, 3 frames can make 9 faults, and 4 frames can cause 10 faults. So the more physical frames we got, more page faults. Second, the optimal algorithm. The optimal algorithm provides a theoretical benchmark. The mechanism of the optical algorithm is it replaces the page that will not be used for the longest period of time. Theoretical significance: it guarantees the minimum possible page fault rate for any fixed number of frames. No other algorithm can outperform it. The fatal flaw. Implementation requires perfect knowledge of future memory references. This is impossible in online system where the operating system cannot predict future process behavior. Since it cannot be implemented, the optimal algorithm serves purely as a benchmark to measure how close practical algorithm like least recently used algorithm or clock algorithm come to perfection.
I will start with LRU algorithm. LRU means least recently used. It removes the page that has not been used for the longest time in the past. It is based on the idea that recent use means future use. LRU gives very good performance and doesn't suffer from Blaire's anomaly. However, it needs expensive hardware support because every memory access must be recorded. Slide 8. Clock algorithm. The clock algorithm is a simple and vertical version of LRU. Pages are placed in a circle and the pointer moves like the hand of a clock. Each page has a reference bit. If the bit is 1, the page gets a second chance. If it is 0, the page is replaced. This method gives good performance with low cost. Slide 9. LFU and MFU algorithms. LFU means least frequently used. It removes the pages with the smallest usage count. The problem is that all pages can stay in memory forever, even if they are no longer needed. MFU means most frequently used. It assumes that pages with low counts are new. However, MFU doesn't match real program behavior and is rarely used. Slide 10. Thrashing. Thrashing happens when a process doesn't have enough memory farms. The system keeps sweeping pages instead of doing useful work. CPU usage becomes very low while disk usage becomes very high. To solve this, the system can use the working set model to control how many processes run page. Page buffering is also used to speed up page replacement. And thank you.
So hey everyone, I'm Muhammed. Let me continue from where my teammate stopped. So in this slide here, we're gonna talk about the Linux operating system and how does the Linux operating system replace the pages and what does it use. So the Linux system uses a hybrid least recently used approach, where it has two main lists, which is the active list and the inactive list. So the active list contains frequently used pages and is protected, while the inactive list contains less used pages and is ready for replacement. So when the system needs to replace a page, it will look to the inactive list. Also, another thing here we have, when a page is used again, it moves back to the active list. So it will become protected. This method gives good performance with low overhead. In the next slide, we have the comparison between different algorithms here. So we have the random access. So in the random access, most algorithms here perform almost the same. In the sequential access, the first in, first out algorithm and the least recently used behave similarly and can be very slow. When the last one in the looping axis, the least recently used and clock perform much better than the first in first out because they keep the working pages in memory. And here for the last slide, we have a conversion summary. So as mentioned, the first in, first out is simple but weak and suffers from Biladis anomaly, as my teammate explained. Also, the optimal algorithm is the most perfect, but we cannot apply this because we cannot predict the future, as we said. But it's only theoretical, and we can use it for the benchmark. Also, we have the least recently used. It's very good but expensive to implement. And the clock is the most practical and is widely used in operating systems. Well, when the least frequently used is useful in some database systems. So we can say that most modern operating systems use hybrid approaches, as we said for the Linux operating system, instead of pure algorithms. That's it for the presentations. This is the summary, the final slide. So the most important points here are: least recently used gives excellent performance but has high cost. Also, the clock and the toolist methods are the best balance between performance and cost, where the first in first out is simple but not reliable. In the future, new memory technologies like non-volatile memory will require new replacement strategies. So that's it for the presentation. Thanks everyone for listening. Hope you having a good day.